For this example, we're asked to look at this problem. Problem is made up of the shaft, a vertical shaft, which is rotating with a constant rate of capital omega. This arm AB is rotating with that shaft, and pinned to arm AB is a second link here, BC, which is rotating relative to AB at a rate of theta dot, which is also a constant. What we want to do is know the angular velocity and angular acceleration of link BC. So if we write this in the context of our observers, what we're going to do is say omega. Well, first let me remind ourselves here that the observer is going to be attached to BC, this guy here. Also going to attach XYZ to BC. So everywhere that BC goes, so does XYZ, lowercase. And big XYZ is going to be attached to ground. In other words, it's fixed. Okay. So omega, which is going to represent the angular velocity of the observer, has two components. One component is this capital omega about the fixed big J axis. And then there's a second component, which is a theta dot about the lowercase k, and that's in the plus sense. So it's good at this point to take note that this is a fixed axis. It doesn't change. Its orientation is always the same. Whereas this one here moves. At the instance that's showing big K and small k are pointing the same way. But some instant after that, that's not true. So that's going to make a difference when we do our differentiation. So whenever I say alpha, which is the angular acceleration of the observer, I simply do a differentiation of that with respect to time. So that's d dt of omega j, big J, plus a time derivative of theta dot small k. As that. So I use a product rule of differentiation. I get omega dot j plus omega j dot. And then I do a time derivative of the second term. So let's use the product rule again. Theta double dot k plus theta dot k dot. It says that big omega is a constant. Theta dot is a constant. So we lose those. This is equal to a 0 because J is fixed. So big J does not change in length. It doesn't change in orientation. So that vector is a constant. The only term that does make a contribution here is coming from k dot. And we know that the time derivative of a unit vector, which is moving along with our observer, is just given by omega cross that same vector, omega cross k. So that's theta dot. And the omega vector we said was big omega, big J, plus theta dot small k, and that gets crossed with k. K cross k, that's a 0. Anytime you cross a vector with itself, that's a 0. So all that's left is theta dot omega big J cross with small k. So now, before we can do that cross product, we have to write both of these in the same set of coordinate axes. Either write big J in terms of small ijk, or write small k in terms of big ijk. Let's write big J in terms of small ijk. We want to find this when theta is 90 degrees, like that. So let me draw the picture here that big I is like this, big J is like this, small I is there, and small j is like that. So for this instant, and only this instant, big J is aligned with small I. So this gives us theta dot omega. J, we said, was the same thing as small I. That gets crossed with K, so I cross K is going to be minus J. So this is a minus theta dot omega small j. And I think we were asked to find both omega and alpha, so let's write omega also in the same frame. So this is omega is equal to, what do we say, big omega, big J, plus theta dot small k. If I write big J in terms of small ijk, that becomes omega small I plus theta dot small k. So there we have it. So I think the key part of this question, as well as many of the questions we're going to be doing, is writing down first the angular velocity, recognizing which components are fixed and which ones aren't. In this case, we had a rotation about a fixed axis, the big J, and a second component, theta dot, about small k. The key here is that small k moves, big J does not. So once you write down omega, then just simply do differentiation. So the differentiation gave us four terms. Two of them, omega dot and theta double dot, dropped out because omega and theta dot were constants. A third term, j dot, dropped out because j is pointing the same way for all time. So all that we were left with was a k dot. We used a result from class that the time derivative of k is omega cross k, and then carrying through that in order to get the angular acceleration of our observer.